All right. Let's get started. How is everybody today? Oh, it has dropped a lot. From the time I got here to the time I walked outside to walk over. Temperature drops. As long as it doesn't rain or snow, since we only have half a roof on our addition right now. We don't want it to completely rain.
Oh yeah, how's the contract?
It's going well. We have more. The framers are coming back on Friday. Hopefully we'll get that roof all done fairly soon. So. All right, who would like to offer a prayer for us today? Thank you.
Dear Heavenly Father, we're so grateful for this beautiful day and that we can all be here together and learn together, and we pray that we'll be able to understand what we're learning and that we'll be able to remember everything and perform well on our tests this week, and that we'll do well in all of our other classes as well. We're so grateful for the gospel, and we say these things in the name of Jesus Christ. Amen.
Thank you so much. Okay. Exams going on. So last day is, you can take it on Friday, but that's a late day. It costs you money, so try to take it today or tomorrow. Please don't talk about the exam to others after you've taken it. We don't want information passing. That's considered cheating. So study hard, pray hard.
Is it Friday after 3 or just any day Friday?
I think it's any time Friday. But you check with the testing center, I'm sure. So I didn't set it up, so someone else in the math department set it up. So any other questions about the exam?
Yeah, it's any time.
Okay. Any time on Friday was the answer to the question of, is it late a whole day on Friday? You have to pay $5 the whole day on Friday? Yes. How many questions? I don't know, there's like 8 multiple choice, 6 short answer, 5 or 6 free response, something like that. But I think some of the questions are multiple. Yeah, or here and then there. Here, quiet everybody. Yeah, like in the front cover of your book that you don't have because it's an ebook. But there should be somewhere in the ebook. If you have a physical copy, you open up the front cover. It has a whole bunch of trivia. But if you've used it in class for an assignment, you should probably. Okay. Right there and then there.
How many hours should we set aside for it?
We wrote the exam to take 2 hours on average, but if you feel like you're a slower test taker than others, give yourself more. Oh. Okay. Oh, great. Okay, so they put on a trig identity sheet on Learning Suite. You remember where on the content page? On the resource page. Okay. Let's hear it for those TAs ahead of the game. They made me look good. All right. Or maybe they make me look bad. So one semester, Patrick of Patrick JMT fame was rated as our 4th best TA, and I was the 5th. You know, I was rated as underneath Patrick. So, all right, let's get started. Simple quiz today. Are you here? Looks like we have a couple people that have chimed in saying they're not here. So, that's all right. You know, gotta fix that. Okay. So here is the question of the day. Oops, not but. All right. So we can actually calculate this. We can do a trig sub, or we can recognize that it's an arctangent thing. Some of you actually might be able to look at this, think for a little bit, and realize what the answer to this integral is. Anyone? Anyone? Bueller? Bueller? Okay, sorry, what? It's pi. So the answer to that is pi. You end up with an arctangent of 1 minus an arctangent of 0, and it's all multiplied by 4. Arctangent of 0 is 0. Arctangent of 1 is pi fourths. The 4 times 4, pi fourths get 2 pi. All right. So why do we care about this? Well, what if you wanted to actually estimate the values of pi, the value of pi? This has actually been a problem throughout history of trying to find better approximations of pi. What does it actually equal? Is it finite at some point? Is it not? So we can actually use numerical integration to not just get an estimate, but to know how good our estimate is. So my question to you is, if we use Simpsons Rule, how many intervals do we need to get within 0.00000000? How many zeros is that? 0. I think I wanted that one to be a 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1/1 of the true value. Okay? So we can do that with an error using the error estimates. So for Simpsons, their estimate is sum k times b minus a to the 5th over 180 n to the 4th. And we don't derive these in class. We just take them. You can believe them. I have done the trapezoidal rule before in class, but so right now, talk to your neighbor and talk about how would you actually go about trying to figure out what n is. What's the number of subintervals we'd need to get an estimate of this integrand up here, to get an estimate of this integral to within 1/1000th of the true value. So just talk. You don't have to start doing it, but talk about what you would do. All right. So of the things that of all of the variables sitting in this expression, which ones do we know right away? We know b and a, so 1 minus 0 to the 5th. Okay. we do know the error that we want. Oh, that's supposed to be less than or equal to, or yeah. So 0.000000. How about 1 over a billion? Okay. Okay, what else do we know? Do we know n? That's what we're trying to find out. Okay. And so the last thing we need to know is what this k is. Okay, who remembers what that k represents? So k is some value that's greater than or equal to the max of the absolute value of, in this case, the fourth derivative of our integrand. Why fourth? So, because anything less doesn't affect the error. These come from, it's easier to see with like the trapezoidal rule. So the furthest you could be off if you were using straight lines, like the trapezoidal rule, it only depends on your concavity, which depends on your second derivative. So what they do is they assume on an interval, or on the interval of your function, what's the largest the acceleration is, and then just assume that it's that acceleration through this entire piece. Even though it might change, this might be the actual value. This might be what it really is. If you assume worst case, you know it would have to end up being a larger error. You'd be further off. And so for midpoint and trapezoidal, you only have to look at the maximum of the second derivative. And the way that these are derived is you assume worst case scenario, and you assume that the furthest off that you are, like the slope is always changing at that rate. So through the whole thing. We won't get into the details, but Simpsons Rule, you have to actually go to the fourth derivative. Third or less, that won't change it. Okay, so who's done the work to actually figure out what that maximum value is for that fourth derivative? That was kind of a joke, because maybe someone has, I don't know. Let's have Wolfram do that for us today. Don't look at the number of tabs I have up here. So my brother sent out a picture of my mom's computer. She had 72 tabs. So now I know where I get it from. So 72 is high for me too. So let's do maximum of the fourth derivative of 4 divided by 1 plus x squared on 0 to 1. So took the fourth derivative for us, and look, it graphed the fourth derivative, and at x equals 0 is where we get the largest on the fourth derivative, and it's a value of 96. Okay? Now, some of you are thinking, Brother Corey, if you're going to use Wolfram Alpha, why don't you just tell it to give you 75,000 digits of pi, because it'll do that, instead of the 9 we're trying to estimate it by. But okay, that's not what we're working on right now. Okay, so sometimes they're not too bad. We might get to a problem today where you can actually do it by hand to find the maximum of the fourth derivative. But this one, the maximum of the fourth derivative on this interval from 0 to 1 in absolute value is 96. So we could use k equals 96. We could also use k equals 100. It's a little more than the max. You just have to have some k that's larger than that. You could pick k equals 100 billion if you wanted, but then you don't really know how accurate you are. So, okay. So now we have by Wolfram Alpha, we're going to pick k equals 96. Now, why don't you guys solve for n? Now you know everything you need to up here to solve for n. So I'm going to rewrite it down here. So as I walked around, I looked on people's calculators. I saw 3 people that had the same value. So it was something like 151 point something, 0.97. Okay, and if we're doing Simpsons Rule, so this is a number of intervals. It has to be an integer. If we do Simpsons Rule, it has to actually be an even number. So we're going to round it up to 152. Okay. So n equals 152. Okay, now your next problem is to actually use 152 intervals to actually calculate what that estimate of pi is by hand. No, just kidding. Let's use Excel to actually do this. But first, are there questions about this 151.97? What was that? Oh, I was scrolling up. That's scrolling up. This is scrolling down. Okay. So I'm going to pull up Excel. Am I good to go? Am I good? Oh, you want to see the integral? So 0 to 1, 4 over 1 plus x squared. So let's pull up a new sheet here. That didn't work. Let's try that again. How come I have a whole bunch of stuff? All right. So we're going to use Simpsons Rule. I'm going to put in just a list of numbers over here, integers, so that I know when I get to 152. My lower bound is 0, and my next x coordinate. Oops. Tell your neighbor what my next x coordinate is. Okay, I wrote down that I need to move over 1 divided by 152. Where did that one? Where did this 1 come from? Someone tell me where this 1 came from. In my numerator, Where did that 1 come from? This is my b minus a. I have a distance from 0 to 1, and I have to divide that by the number of intervals. This is really that 1 over 152 is just my delta x. So I have b2 plus delta x. And I can keep adding delta x's there. Now what's my function value? Now I'm going to say, take 4, take 1 plus whatever this number is, square it, divide that into 4, and those are going to be the heights of all my rectangles if we think of it like left hand or right hand estimate. And then I have my Simpson Rule multipliers. 1, 4, 2. What does it do from there? Yeah, it's not gonna. I don't think it's gonna do this the right way for us, but I might have to give it more of a pattern first. Yeah. 4, 2, 4, 2, 4. We'll see if Excel's smart enough to do this. Otherwise, I should have picked a smaller value then. Nope, it didn't like that, did it? Okay, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. Okay. And my computer's a little small. What did I end up on? 2, 4. All right, so you should be thinking about yourself, what should Brother Corey do after he does this insane thing that he shouldn't have done in the first place, which was pick such a small error estimate. But what should I be doing next? Like if you were in charge of the computer, think about how you would finish the calculation. Okay, so I got all my 2s and 4s in there. We're doing 152 intervals, so I need 153 values. So if you have 152 spans, like fence spans, you need 153 fence posts. So that's why this number is 153. But I end up on 1 here. Right, I'm going 0 to 1. My very last value should be, x-coordinate should be 1. Okay, and I did change that 1 at the very end, right? So here's the 1 right there. So it's 2, 4, 2, 4, 2, 4, 1. Okay, now I multiplied my function value times the Simpson Rule coefficients, and now I need to add those all up, and then think about what I would do next. Does that look like pi? Nope. I'm not done yet. I've added those up. What do I have to do? I have to multiply by delta x. So that's going to be this cell times 1 divided by 152. Or just divided by 152. Hey, we're closer, but what else do we need to do? Divide by 3. That 3 comes from the Simpsons Rule formula. So this divided by 3. Hey, how do we do? And look at that. The value that that Excel has up to that many digits. How far do we go there? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That is an 8 digit there. So, or within 1 billion. So, how does it? When you type in something like sine of 3 degrees on your calculator, or like the natural log of 2, how does your calculator actually know what to spit out? How does it actually find that value, that decimal approximation? He said it does something more complicated than this to get it even closer. Does it have a database? So if you wanted to have this accuracy, just for like a function like sine, to have all the inputs and outputs from sine to 0 to 1, 0 to 1 radian, it would take 20 gigabytes just to hold that. So it doesn't have all of those hardware in it. It has to do something else to calculate it every time. Otherwise, you just need. You can't calculate every possible thing you might punch into the calculator and store it. How do people go about doing it? Calculus? Yeah. Part of it depends on what you punch in, but some of it actually does things like this, numerical integration. If you have something, if you have a numerical integration function in there, but how it does it if you just punch in like sine or something, we'll get to that in a couple of chapters. But it does use calculus. So, and they do use error bounds to make sure that they are out far enough so that they're not lying to you when you do an estimate. That last digit they show you, you're never quite sure because it might be rounding. But all right, questions on numeric integration? Questions on error bounds or the techniques? Okay. So how do we find the maximum value of any function? You can take the derivative, set it equal to 0, and solve. So if you're trying to put, you could go to the fifth derivative and then set it equal to 0 and solve. Generally, these are, what are the endpoints on your interval is going to be on that. But here, let me give you a different one. You guys, if we did Simpsons Rule on this next one I'm going to throw up, I'm going to have you guys find by hand what your K would be. All right? What would K be for that? You don't need Wolfram Alpha to do this. The question was, is Simpsons Rule the only rule that you got to put through? Yeah, the three error formulas that we have, Simpsons goes to the fourth, trapezoidal and midpoint, no one goes to the second. Okay, so I took the fourth derivative. This is what I got right here. And on my interval from 1 to 3, it's not the maximum value everywhere. It's on the interval that I'm trying to calculate the definite integral from. So on that interval from 1 to 3. What is the largest value I could get if I have 24 divided by x to the fifth on that interval? 24. Because to maximize that, I want to make my denominator the smallest. The smallest I can make it is 1. You plug in 1, you get 24. So that's an example where it doesn't take too much work to figure out and reason through what your k is. So, all right. Great. Other questions about numerical integration? So the next project that we have, the one that's due next Thursday, you get to do your own numerical integration project. So I encourage you to do something with data, kind of like my failed attempt with the data with my rubber band yesterday, or 2 days ago. So there are a bunch of examples that I put on Learning Suite. Try to find something that's meaningful to you. I had one of my computer science students, he had data on how fast data was downloading to his computer over a certain interval. The rate is not constant. And then he numerically integrated it to find out how much data he was downloading over that time. I had another student that loved to work out. And he does this lift with his hex bar. He stands in the middle and he gets this rubber band and attaches it to the bar. And so he pulls it up, the rubber band stretches. And he wanted to know how much work he's doing when he lifts that up. So he got a friend with a clipboard to stand there, and they had a measuring tape. So he'd pull it up like, you have to get a scale. You have to stand on a scale to get an idea of the force. So he stands on the scale, gets the rubber band underneath the scale, pulls it up every 6 inches, has his friend write down how many pounds of force he's putting on the scale to figure out how much it is. So find something fun. Find something has meaning to you for those projects. There are some other examples in the project. Okay, let's jump to 7.8. Oops. Okay, does this look familiar? You guys did this in a lab several weeks ago. What problem were you working on for this one? We were trying to find escape velocity, right? We were looking at how much energy, just estimate how much energy it takes to move an object from the surface of the Earth to infinitely far away. Okay? What's weird about this integral? you have a bound that's infinite. Okay? These come up surprisingly often. Okay, anyone know what this represents? Represents the next calculus problem. This actually is connected to the numerical integration problem because you can't find an elementary function that you can take the derivative of and get e to the negative x squared. So I guess you can't apply the fundamental theorem of calculus because you can't find an antiderivative of that. So you have to do it numerically, or do some really, really tricky math. This actually represents the percent of males in the U.S. that are higher than 6'6". Are you taller than 6'6"? Oh, okay. It turns out statisticians use these all the time because you get distributions that are infinite and you calculate for the probability of infinite. So economists care about infinite integrals, so they're worried about what happens long term. So you're worried about how things are going to happen as time goes to infinity. So these come up. This is one kind of what's called an improper integral. So improper integrals. It's where you either have one bound, your bounds are infinite, or your integrand is infinite. Oh, let me do that better. Problem with trying to write legibly is I have to be able to spell it right. So what's an example of that? So just going 0 to 1 of 1 over x dx, or 0 to 1 of the natural log of x dx. We have problems at these lower bounds. It's 1 over 0, or here, the natural log of 0, it's undefined. At the graphs of these, natural log looks like this. The graph of the 1 over x looks like this. So at one of our bounds, we've got a problem. Infinity, negative infinity. So how are we going to handle these? Have I mentioned before that calculus is the taming of infinity? Some people, some mathematicians will say that that's the field of calculus is taming infinity. How do we tame infinity in calculus? We use limits. So limits are the main tool we use in calculus to tame infinities. So we actually rewrite these as a limit of a definite integral. So here you'd have the limit as x goes to 0 from the right. No, limits again. I thought we were done with limits, Brother Corey. Oh, I didn't mean x. Yep, you're going to brush up on your L'Hopital's rule. So 1 of 1 over x dx. And this one is, it doesn't matter what variable you pick here. Oops, it goes from. So we set these up as definite integrals with bounds, and we take limits as those bounds go to 0 or bounds go to infinity. So it's enough of me talking. Let me give you guys a problem to do. So here we've got the curve 1 over x. Here we've got this shape. How long is this shape? Very long. It's infinitely long. So you might think, because it's infinitely long, how much area do you think we'd have? Infinite area. Why don't you guys go ahead and calculate that? Okay. Set up. I'll write it here as a limit. The limit as a goes to infinity, 1 to a, 1 over x dx. Okay, why don't you guys calculate that? All right. So the antiderivative of 1 over x is the natural log of x going from 1 to a. So limit as a goes to infinity of ln of a minus ln of 1. What's the natural log of 1? 0. So now we have to figure this out. What is the limit of the natural log of a as a goes to infinity? It diverges. Okay. So why would you say it diverges? We haven't used that language yet in this class. So what was that? Oh, okay. So it diverges how? Where is it going to as it diverges? Infinity. Are you sure? How do you know? How do we know the limit of the natural log of a as a goes to infinity is infinite? She said graph it, but I actually find that hard because it keeps leveling off flatter and flatter, and I'm not sure if it'll ever kind of stop leveling off and not get higher than a certain number. So here's one way to think about it. One way to do this is to think about it in terms of an exponential. The natural log of a equals what is e to what power is a. And for a to get arbitrarily large, this exponent also has to get arbitrarily large. Right? There's no exponent I can plug in here and get larger than any number I could give it. So it actually has to go to infinity. All right, so we found out this infinitely long figure here has infinite area. So what if we take that area and spin it around the x-axis, revolve it around the x-axis, and get a volume? How much volume are we going to have? Okay, why don't you guys calculate that? There. I'm going to do it up here. I just blanked the screen, so you can't follow. You have to do it yourself. All right, we're running out of time. Let's finish this up. I know some of you aren't quite done. I'm not quite done either. So, found the antiderivative of 1 over x squared. The volume is the radius, which is 1 over x squared. It's my function value times pi. So my r squared. I set it up as a limit, so my upper bound is going to infinity. And I get minus a negative pi there, so I end up with a plus pi. And what happens with this here? As a goes to infinity, I go to 0. So I end up with just pi. Does that make anybody feel uncomfortable? So we have this infinite area, we spin it around, we get finite volume. How does that work? Next time we'll also do the surface area. What we got a guess on the surface area? Finite or finite? We'll do it next time. Okay, have a great day. Thank you. You're welcome.
Sometimes when we're doing like volumes and stuff like that, and you just get like a number, are there ever any like units associated with like, those volumes, or is it just like a number?
It's units cubed. So whatever units you were using, we are not really good in math at putting down.
No, it's just a number.
So since this is a volume, it is a units cubed, and the units actually help. Like, because
if it was like a massive, like an infinite unit, then what if it was the same thing like pi?
Yeah, hold on, let me